Hello, my name is Philip Skeps, and I'm doing research with the Salmonet Group. This year's objectives were to try and link molecular dynamics simulation data of DPPC to experimental data to create an equilibrated bilayer for further modification into a monolayer and understand particle tracking. The alveoli of the lung contains a lung surfactant air interface mostly composed of DPPC. During the pandemic, we have been exposed to a greater amount of graphene contained in many brands of mask. Also, in the future, graphene may be used as particle sensors for abnormalities in the lung. Therefore, it is important to understand its toxicity in the lungs. The LAMPS MD software was utilized to model both monolayer and bilayer systems. TIP 3P water was used in both models in accordance with the CHARM 36 lipid force field. Periodic boundary conditions were used in both models, and both simulations were thermostated to 323 Kelvin. 72 total lipids at 30 water molecules per lipid. Initial structures were created using CHARM GUI. An MPT ensemble barostated to 1 bar for 20 nanoseconds was used to collect data on the area per lipid. An NVE ensemble was ran for 10 nanoseconds after the NPT ensemble to determine how equilibrated the final structure was. The monolayer system was generated on both sides of a water slab, and a large vacuum space was added to prevent interactions between periodic images and the z-axis. An NVT ensemble was ran for 20 nanoseconds. The area per lipid in the system was held constant at 80 angstrom squared. The particle tracking system consisted of two 68.7 angstrom diameter graphene particles at a water-air interface. Only one particle was tracked during the simulation. An MVT ensemble thermostated to 298 Kelvin was ran for 50 nanoseconds. This system utilized SBC/E water, the Ariba force field for graphene particles, and Leonard Jones for water and graphene interactions, as per the previous student who worked on the project, Andy Bay's suggestions. In the bilayer model during NVE, there were small changes in temperature and pressure. This is shown by the extremely small slopes of the trendline equations. This demonstrates the energy of the system remained relatively constant during NVE, and the ensemble did not have to regulate the energy too much by altering the temperature and pressure. The system is now ready for translation to the monolayer system. During the NPT ensemble of the bilayer system, the average area of the last 18 nanoseconds was 63.4 angstrom squared, which matches the experimental area per lipid at 323 Kelvin, which is 63 angstrom squared. This correlates to a 0.6% error, which was very acceptable. As shown below by the variance in tail order in the DPPC, the molecules are in the liquid crystal phase, further validating the lipid force field for bilayers. The monolayer had an average surface tension of 44.1 millinewton per meter, which deviates from the experimental surface tension of 54.9. Although this is very far off with a percent error of 19.7%, this is expected as monolayer systems are sensitive to long-range Leonard-Jones interactions. These long-range interactions are not implemented in LAMPS MD for the CHARM force field yet. This value, however, matches documented simulation data. Also, the system may not be fully equilibrated because it is difficult to equilibrate air DPPC interfaces. The problem is solved by first equilibrating a bilayer system and translating the lower leaflet in the Z to form a closer equilibrated monolayer. And the preliminary tracking system, it is shown that graphene exhibits Brownian motion by the region of the graph with a slope of 1. As shown in the graph below by David Goggin, as DPPC concentration increases, the MSD and therefore diffusivity decreases. In the future, I hope to see this trend on a much smaller scale during my simulations. In the bilayer system, a well-equilibrated final structure was obtained and is ready for translation into a monolayer system for further testing. The monolayer system shows deviation from the experimental data as expected and matches well-documented simulation data. Preliminary particle tracking is now more understood and can now be utilized in future simulations. In the future, I hope to design a program that can turn an equilibrated bilayer system into an equilibrated monolayer system for further testing, as shown in the image above. I also hope to incorporate long-range interactions for the CHARM force field into LAMPS and utilize these interactions to obtain more closely matching simulation to experimental data. Lastly, I hope to utilize my newfound skills in particle tracking to calculate the diffusivity of graphene particles across the DPPC monolayer and hopefully match experimental data calculated in the lab by the Salmonet Group.